Event-driven architecture is quietly running some of the biggest platforms on the internet. As microservices, big data, and real-time features become the norm, companies need a way to let dozens, sometimes hundreds of services talk to each other without falling apart under their own weight. In this video, we'll break down what event-driven architecture actually is, why it's taken over modern system design, and how companies like Netflix and Uber use it to process billions of events a day. Let's get into it. Start with the traditional approach. Service A needs something, so it calls Service B directly. B processes the request, sends back a response. With 2 or 3 services, that's completely fine. But add more services, and the problem isn't gradual, it's exponential. Every pair of services that need to talk now needs its own direct connection, its own request format, its own response format. A handful of services might mean a handful of connections. Dozens of services? Now you're maintaining a tangled web where every service has to know about and directly call half a dozen others. And that web is fragile. Change one service, even slightly, and you risk breaking every other service wired directly into it. This is called tight coupling, and it's exactly what makes systems hard to scale, hard to update, hard to reason about. Event-driven architecture exists to cut that web apart. Instead of services calling each other directly, they react to events. That one shift changes everything downstream. So what is an event exactly? It's just a signal that something happened. A user clicked a button, an order got placed, a sensor sent a reading. In this model, services don't ask each other for things directly anymore. They just announce what happened, and whoever cares, listens. 2 roles make this work. Event producers create events. Take an e-commerce app. When a customer places an order, the order service produces an event, something like order placed. Event consumers are the services that react. The inventory service might consume that same event to reduce stock. The shipping service might consume it too to kick off fulfillment. And here's the key part. The producer and the consumers never talk to each other directly. They don't even know the other exists. As long as they're both connected to the same messaging system, the event just flows to whoever's listening. Let's look at how Netflix actually uses this. Netflix processes over 1 trillion events a day. Streaming behavior, analytics, recommendations, system health, all of it running through an event-driven backbone. Every action you take on Netflix produces an event. Start a new show, event. Rate a movie, event. Pause halfway through, event. That signal fires in real time and gets picked up by whatever service cares about it. Start watching something new, and the recommendation engine consumes that event immediately, updating your suggestions before you've even finished the episode. Netflix also uses this pattern to watch its own infrastructure. If a service starts slowing down or fails outright, that itself becomes an event, and a monitoring service consumes it, alerting engineers or triggering automatic recovery. The result? Netflix handles enormous real-time load, scales each service independently, and personalizes your experience instantly, without any of these services being tightly wired to each other. Uber runs on the same core idea at a similarly massive scale. You request a ride. That single action produces one event, ride requested. And here's where it gets interesting. Multiple services consume that exact same event, each doing something completely different with it. The matching service consumes it to find a nearby driver. The ETA service consumes it to estimate arrival time. The pricing service consumes it to calculate cost based on distance and demand. 3 totally different jobs, all triggered by the same one event, all happening independently. Uber also pulls in a constant stream of location pings from drivers and riders' apps. Those signals feed straight into matching and pricing, spotting when supply and demand are out of balance in a neighborhood, or when 2 ride requests land near the same driver. All of it, ride requests, location pings, pricing shifts, flowing through the same event-driven system, built to handle high frequency and stay resilient when parts of it fail. Now, a quick distinction, since these terms get mixed up a lot. Event-driven architecture, service mesh, and the sidecar pattern all show up in microservice systems, but they solve different problems. Event-driven architecture handles asynchronous, event-based communication. Service mesh handles synchronous, direct service-to-service calls. And often, a system needs both, running side by side. Back to Netflix as the example. Watching, pausing, rating, all asynchronous events, flowing to recommendation engines and analytics in the background. But Netflix also needs synchronous calls, fetching data from a catalog service, for instance, where you need an answer right now. That's where a service mesh steps in, managing retries, load balancing, and routing for those direct calls. And underneath that service mesh, each microservice typically runs its own sidecar proxy, a small companion process handling things like encryption, logging, and service discovery, so the main service doesn't have to. Scalability is the biggest reason companies adopt this pattern. Because producers and consumers are decoupled, each service scales on its own, exactly what you need when traffic spikes hit unevenly across a system. There are two broad styles of event processing. Simple event processing, where one event triggers one straightforward reaction. Order placed, update stock, start shipping. Clean, direct, easy to reason about. Complex event processing goes further, aggregating multiple events over time to detect patterns. Uber's dynamic pricing is a good example, looking at traffic, demand, and driver availability together across many events to decide when to trigger surge pricing. Every event-driven system needs a few core pieces. Producers, the services generating events, whether that's a user action or a system change. An event broker sitting in the middle, something like Kafka, RabbitMQ, or a cloud messaging service, queuing and routing events from producers to consumers. And consumers on the other end, reacting however they need to, writing to a database, triggering another process, calling another system. You also need clear event contracts, a defined shape for each event type, so every consumer knows exactly what fields to expect. An order-placed event, for instance, would reliably include an order ID, product details, payment status, so nothing downstream breaks from a surprise. None of this comes free, though. Ensuring events get processed in the right order gets genuinely hard at scale. And because events can be retried after a failure, you have to guard against processing the same action twice. You really don't want stock deducted or a payment charged more than once. Managing consistency across many independent services also takes real design discipline. Real-time doesn't always mean instantly consistent everywhere at once. A few tools dominate this space. Apache Kafka, a highly scalable platform built for real-time event streaming, used by companies like LinkedIn and Uber to handle millions of events per second. Cloud-native options like Amazon's managed messaging services fit naturally into AWS-based systems. And RabbitMQ remains a lightweight, easy-to-set-up choice for smaller-scale systems. As Netflix and Uber show, event-driven architecture isn't just a trend. It's the backbone underneath systems built to handle billions of events every single day. Before you go, 10 interview questions on screen. What's the core difference between request response and event-driven communication? What is tight coupling and why does it get worse as services multiply? What's the difference between an event producer and an event consumer? Walk through one event and how multiple consumers can react to it differently. What does it mean for producers and consumers to be decoupled? What's the difference between event-driven architecture and a service mesh? What's the difference between simple and complex event processing? What is an event broker, and name 2 examples? Why do you need defined event contracts? And what are the main challenges of event-driven systems, and how do you handle duplicate event processing? Answer all 10 out loud, and you actually understand this. If this helped you understand the pattern better, hit like and subscribe, and let me know in the comments what architecture pattern you want broken down next. Thanks for watching, and I'll see you in the next one.